So let's get started. What I'm really talking about today in engineering simulation is mechanical engineering simulation. I'm limiting it to that area because the areas of electronic simulation, systems level simulation, and so forth are worthy of many webcasts or webinars in their own. So I'm limiting this one to the one that I actually have spent more of my time in than the others. And technically, this is what it is. It's just the use of applied physics, numerical methods, algorithms, and computers to model and study the functional behavior of multiple manufactured instances of proposed physical product and process designs. That's a key point there in bold, because most of what's done with MCAE, not all, but most, leads to designing something that gets made multiple times, either tens, hundreds, thousands, tens of thousands, or even millions, or maybe in one case billions if you count the diapers manufactured by Procter & Gamble, which are in fact subject to MCAE simulation in their development. So anyway, that introduces additional concerns and considerations on what the results of a simulation tell you in terms of the variation of different manufactured instances, for example. So it's key to keep that in mind when you're doing MCAE. Also, there's a lot of different terminology. MCAE is one that's been used for a long time. Functional virtual prototyping was used in the early 2000s. It's used a little less now. Digital prototyping, very similar to that. Simulation and analysis is a term coined mainly, I think, by SimData to describe the same area, and they have a practice, an active practice in that area. For the purposes of this presentation, any of those are the same. I'm talking about engineering simulation in the mechanical industries. The topics I'm going to cover here are a little bit of a historical perspective, how MCAE transitioned from primarily a technology topic and subject and activity to one where business more and more drives it today. Vendors who came into existence with that technology to create software and related solutions for industry have grown up, and some have consolidated, others have emerged more recently. So it's still a very active pipeline, I would say, of companies at all levels of size and maturity in the MCAE vendor world. I'm going to talk a little bit about the structure of the MCAE vendor industry, who are the major players, what relationships do they have with each other, some technology issues, and the rest will be covered in the next webcast on the 25th, where I talk about where all this is leading to in the future, in my opinion. So I found this is an interesting way to describe what's called the engineering simulation food chain, where you start out with, as I said in the earlier slide, physics, math, computer science, all enter and combine into research that develops methods for doing engineering simulation. Those methods generally fairly quickly turn into some kind of software, either prototypes to test the methods or software that's meant to be a little more robust and used eventually by end users in industry. That transitions into a true focus on the software development, then a focus on the applications. Of course, the applications have played a role from the very beginning in driving what the research is done on and what kind of software gets developed, because it's always targeting some kind of real-world physics problem that people want to be able to understand better because it relates to the products they're developing. When you really get into the software being applied to the applications, current computer hardware and infrastructure industry and considerations enter into the picture more directly, even though computer science was way back in the beginning of that food chain. And then finally, all this is pointing towards the use of simulation for product and process improvement. That's really the goal here. In other words, for engineers to get insight, to have that aha moment where, as a result of simulation, they say, now I see how something is going to behave that I'm working on, or I see much better how it's going to behave, and that allows me to make better decisions in what I'm designing. The old cliche, the purpose of computing is insight, not numbers. So anything that gets you away from drowning in numbers and towards insight is a very important part of that food chain. The industry itself depends on your perspectives. You know, the old cliche about the blind man trying to describe an elephant, and depending on where they're touching the elephant, it has a very different feeling, or they have a different impression of what is an elephant. And we have sort of the same thing here, whether you're a veteran of this industry, you're an early stage participant, or you're a very recent participant just getting into it. And the roles of these various entities that play in this food chain, I'm going to show here just as a background to where then I'm going to focus a little more. You have at this end, of course, universities and government laboratories primarily. Clearly, some software vendors are also involved in some of that very basic research if they have the money and the bandwidth to do that. But in general, it comes from universities and government labs. Then the independent software vendors pick that up in the form of collaboration, in the form of funded research, or just taking the published technical work papers and then implementing them in software, sometimes taking software that was developed in a research mode and making it production ready, commercializing it. But anyway, that's their emphasis, and they go on into being involved in applications because that's what drives the software development if it's going to be useful for industry. They have to understand the key applications that they're targeting, which is why a number of software vendors have consulting arms that represent anywhere from 10 to 30% of their overall business, because that's their proving ground as such with real industry problems. As you get into the application area there, you see that computer hardware and infrastructure enters in, that the software vendors also have to interact with and have partnerships with the various computer hardware companies and infrastructure companies. You get a lot of engineering consulting services. As I just mentioned, the software vendors themselves have consulting services, but there are quite a number of independent companies, large ones in some cases, on down to one-man bands who are experts in applying a particular technology like finite element analysis or computational fluid dynamics to certain problems in a certain industry, and they will make a good living and stay up to date on exactly what they can do in using that technology to solve problems. They also interact with computer hardware and infrastructure companies because they need appropriate hardware to run the simulation on in the problems that they're solving for their clients. And then finally, of course, the big payoff are the end user industries, where all of this, hopefully, if it's all been done right along that food chain, leads to productive use by more and more people in end user industries wherever simulation can, in fact, provide additional insight. That's a whole separate topic that I'll get into more in the next webcast on the 25th as to what are the trends there and what are the enablers and so forth. So here's what I'm focusing mainly on, what you see in the green oval there, both in this webcast and the next one. So here's a little 5-cent tour, as I call it, or 5 euro cent for those of you listening in from Europe, or some number of yen or whatever, renminbi. This is the short tour going back to the 50s and 60s, where basic R&D work and the first very simple software programs were done, mainly in the aerospace industry, or ironically in the civil industry in frame and truss structures. Boeing, MIT, NASA, European Space Agency, and others were key players and entrants that early on. The sort of seminal paper on the finite element method actually came from 5 authors at Boeing in 1956, and they continued to do their own development. Also, a number of aerospace companies pushed NASA to get into the game, and NASA put out an RFQ, which led to the funding and development of Nastran, which I'm sure a lot of you are familiar with, back starting in about 1966. MIT started developing engineering software for civil engineering in the early 60s already, and it got much more intense in the late 60s. I was, in fact, as a student there, involved in some of that back in those days. And I could go on here, but it's not as critical as saying, okay, where did this go to? Mid-60s to 70s, the basic methods for MCAD, which was really computer-aided drafting, came into play, which provided better information on geometry for doing simulation, and as well as early commercial MCAE software came into being around that time. And of course, the emergence of sufficient compute power to allow somebody to do any kind of reasonable simulation. So companies like MSC, SDRC, ANSYS, Abacus, Mark, MathWorks, and others were founded during that time frame. As you see, and I'll mention it later, a number of these have in turn been absorbed into larger companies as the industry consolidated into the bigger CAD and product lifecycle management industries. The 1980s saw MCAD change from the D for drafting to the D for design, with true solid modeling, which was then really a much better basis for starting with solid models as a basis for meshing and doing finite element analysis or computational fluid dynamics. That in turn, plus a lot of work on the user interface, made much more user-friendly MCAE in the form of products like SuperTab, Patran, and so forth that came into their own in the 1980s. The corresponding accessibility of computer power in workstations, a couple of major companies that were founded then to put workstations and small servers on the market. Ironically, those companies generally do not exist anymore. They either disappeared or got merged and absorbed into bigger hardware companies. Product data management was seen as an issue, which helped bring focus to this whole area of MCAD and MCAE and other related things. Product information management, very similar, recognition of the mushrooming data being created by some of these computer-aided tools. During the 80s, companies like LMS, which is now part of Siemens PLM, RASNA, which is now part of PTC, EXA, which I didn't list on the slide, but they were founded in the late 80s, are now a public company, and so forth. So there's more vendors started appearing during that time period. Then in the 1990s, you really started to see the true linking of solid modeling, MCAD, to MCAE in wider production use. More and more of the CAD and PLM companies started cooperating with CAE companies to produce bidirectional interfaces and the ability to pass CAD geometry in a form of solid models to CAE programs for applying loads, boundary conditions, pressures, whatever, and meshing, and then running the simulations. And the whole issue is related to how clean does that geometry have to be, who's going to clean it up, the CAD companies or the CAE companies. All those issues began to be recognized, and efforts were, progress was made in starting to deal with those. Key aspect also, which laid the groundwork for optimization, is the idea of variational modeling or parameterized CAD models. Parametric technology as a company was founded based on that new concept. Others followed with quote variations on that, pardon the pun, and had introduced variational versus parametric, but they all in some form or another had the ability to create solid geometry that was in some form variable or parameterized, which then means when you're doing simulation, you can in fact, on top of that, create optimization loops where some of those parameters are the targets of an optimization algorithm and then get changed back in the solid model and then run through again and so forth. Also, much greater computer and communications power appeared during the 1990s, both in terms of more powerful PCs, client-server networks, and so forth. Any one of these historic decades here is really a subject of an entire webcast in itself. Late 1990s, the big difference there was that the internet or World Wide Web really came into its own. What that effect was on MCAE was really that most of the vendors developed pretty good websites for providing information, examples, tutorials, whatever, but they weren't yet offering any software through that mode. That was and is to come later in the whole picture. Okay, into the 2000s, the millennials, new challenges, of course, which existed prior to that, were now being focused on as some of the other challenges were being taken care of well enough, quote. So discovering and overcoming these new challenges like interoperability of different CAD systems with MCAE and with each other, standard attempts to standardize some of the file transfer, input-output more thoroughly, collaboration issues, both in MCAE as well as in the broader PLM market, and emergence of MCAE as a significant player or component in this bigger product lifecycle management market. Daratech back in the early 2000s claimed that it was about 25% of the PLM market by revenue. Whether that's true or not and what it is today isn't as relevant as realizing that it's in that type of magnitude. It's in the 20s to 30%. And that makes it important for the bigger vendors in PLM to have a piece of that action. And then now we have the decade that we're into now with 3 to 4 years, and simulation data management, simulation process management started to get more attention. Optimization itself became more productive. A few other companies started doing optimization, developing software. The idea of democratization or making simulation available to many more engineers started to be a topic, and I'll say a lot more about that in the next webcast on the 25th. Software as a service, the whole idea of offering up simulation software via the web, via a portal, so that the user only needs a browser and a fast internet connection to do MCAE. That is clearly now a hot topic. I'll have more to say about that in the next webcast. The cloud is very much related to that, and also the idea that the typical physics being done in MCAE for decades, which was either solid mechanics or fluid mechanics or heat transfer, is now more and more being done together or by software that can do it together. And in addition, electromagnetics and other things enter into that picture. So you have multi-physics, you have multi-fidelity, which is a whole other dimension of the multi, and that's different, in fact, than multi-scale. And I won't get into the details of what those differences are, but those are 3 different terms, and software can address one or more of those different multis in a software package. And I will say a little bit more about how each of those is progressing in the next webcast. Okay, now that was a historical advancement. Another thing to point out is a quote that I first heard from Joel Orr, but I think he got it from somewhere else, but I'll give him credit for making me aware of it. The great quote that says, "The future is already here, it's just not evenly distributed," meaning that the way in which MCAE has advanced over those decades doesn't mean that everybody is doing it the way it can be done here in the in this decade. Some people are still just getting into it, which would put them back really in the 80s and so forth. The same is true here with industry. You don't have a uniform advancement even within any given industry. So having made that qualifier, let's take a look here and just in general say that, as I said before, in the historical summary, that MCAE really started in aerospace in the 50s and 60s. Automotive actually picked that up fairly quickly, and in fact seems to have advanced more quickly in that more automotive companies were using commercial software and putting more requirements onto the commercial software developers even than the aerospace companies were. By the late 70s and into the 80s, some of the aerospace companies kept developing their own in-house MCAE, and that was in general a losing proposition because much more money could be invested in good commercial software that got a lot more widely used by a broader segment of industry. Turbo machinery came along in the 80s and 90s. It sort of straddles the fence between it being an industry or an application. You can see some companies that just develop some kind of turbo machinery, and then there are other companies where turbo machinery is a part of many things they do in the aerospace or the automotive industry, like turbochargers, or in power generation and so forth. Electronics came along a little later from an MCAE point of view, even though from an ECAE point of view it was fairly active and mature by then. As the printed circuit boards got smaller and the chips got more powerful and gave off more heat, it became more and more necessary to do more detailed electronic cooling studies. Packaging is very much related to that. How densely can you package a board? Also the drop testing of packaging, electronics packaging that's supposed to be robust under rugged conditions. All of that started being simulated in the 90s and the 2000s. A key company that was founded around that, the beginning of the 90s, late 80s, was Flowmerics with Flowtherm, which really dominated the electronic cooling market using CFD during the 90s. Small and medium businesses, or small and medium enterprises, SMEs, as they're fairly interchangeable, in the manufacturing, general manufacturing areas, and consumer products started to use more and more MCAE in the 2000s. And also chemical processing, which overlaps with energy in the oil and gas area in particular, and oil refining, also got more and more into MCAE in the 1990s and kept on going in the 2000s. Oil and gas, as a part of that, was a little late coming for many reasons. I won't go into all those now. So it really started seeing more use during all of the 2000s. So what were the typical historical obstacles, and what are the steps to further business impact of MCAE that drove both that historical overview that I showed, as well as the different industry penetrations? Well, first of all, everybody said, can we trust the results of simulation? The old cliche of, everybody but the test engineer believes the test results, and nobody but the analyst believes the analyst results. Well, that's not true anymore, but it was a guideline that made people realize they had to do a lot more to convince people to trust the results. And that led to improving the accuracy of methods versus traditional physical prototype testing. And that was the first obstacle to overcome. Then you had, okay, we now believe they're accurate enough, but can we get them in time to impact design decisions? I mean, there's a certain timeline in companies where the results from simulation need to be known in time to give somebody the right insight to make a better decision. So you have the digital processing communication speed had a lot to do with getting those results in time. Also organizational issues. Then the question that was much more organizational was, is it easy enough to use for the average mainstream product development engineer? That in turn had to do with graphic speed, power, and ease of use, the human interface, which related to the previous point. If you can't do the simulations quickly because you're fighting with the ideas of how to apply the loads and boundary conditions and create the mesh in a clunky user interface, then you're not going to get results in time. Finally, everybody was using a lot of different tools and different groups even, and they asked how much time is lost in between the use of individual MCAE tools, which again slowed down getting to that bottom line, how does it impact our business? So incompatibility of tools and data, interoperability and integration issues all played a role there. Finally, how do we overcome the sequential silos preventing multidisciplinary upfront MCAE? That was because of how companies were organized from the pre-simulation days, and what changes had to take place in both the mindset of engineers as well as the management of how those engineers would be organized, which then had a lot to do with business processes in product development. Then related to that, of course, was how do we overcome fear of change and risk aversion? We all know that engineers are extremely risk averse, and so a lot had to do with the company culture related to introducing, accepting, and embracing MCAE. And finally, making that all visible to upper management to answer their question, which is the only thing they care about ultimately, is what is the business payback? In other words, getting executive vision and top-level buy-in to up to the level of enthusiasm, not just acceptance or, for the value, strategic value of MCAE, and that's an ongoing process today. You know, you have some companies that are highly doubtful at that level, and you have others that are enthusiastic right up at the CEO level. The most obvious one that comes to my mind all the time is the CEO of Procter & Gamble, who has gone on record of saying that CAE is a key part of their business. These first four, maybe slightly into the fifth one, were mostly technology issues. The ones after that became more and more business issues as well, not totally, but business tended to dominate as everybody tried to progress through those seven. The progress through the 7 steps varies by industry: aero, auto, turbo, energy, and consumer products, as I said in a previous slide, and also something to do with the company size and the role of the company, meaning are they small to medium enterprises, are they the major OEMs in the automotive and aerospace industry, or are they suppliers to those major OEMs? And that determined a lot of how they progressed through those 7 steps. It varies by company within the same industry. There's leaders versus laggards. Michel Boucher of Aberdeen did some interesting studies here in the last couple of years to get some data on some of that, and you ought to take a look at that. Go to the Aberdeen website if you haven't seen any of that. There's some good information there. Today, progress doesn't, in my opinion, vary significantly by industrialized geography, the so-called first world. Western Europe, North America, and Japan, Korea are all basically at the same point, even though Japan and Korea had a slight lag way back in the beginning, but they caught up. And of course, the BRICS, as they're called, Brazil, Russia, India, China, are catching up very fast. Okay, the MCAE industry today, it's obviously, as I said, complex, diversified, and in some ways not well tracked as an industry. So you've got the fact that a number of us feel that it's at least a $2.6 billion global annual revenue industry, but a lot of that depends on who you ask and how many companies of which kind are included in that number. I'll mention in another slide very quickly a big chunk of that comes from one company that may or may not be considered MCAE. In general, we believe that it has about a 15% growth rate that varies over various different companies and is a little hard to measure because a lot of those companies are private, don't publish their results in any way. There's at least 80 vendors, MCAE vendors, from big companies of 800 million US dollars annual revenue and greater down to a whole bunch that are less than $1 million. Some of those are embedded in, some of those vendors are actually parts of larger PLM vendors. Some are standalone vendors, and they serve industries and customers from huge industries of multiple hundreds of billion size customers down to customers who are also less than $1 million in revenue. Some of the category consolidation that took place is shown here. This is actually an old slide originally from the Chasm group, and it was used by Deratech around 2000, 2001, 2002. But it shows already at that time that a lot of these older areas that were considered separate have come together. I won't go through this whole slide in detail. It's fairly clear that at one point a whole bunch of stuff came together under this umbrella called product lifecycle management. That's where CAE finds itself today. There's both a good news and a bad news side of that. The good news is it gets a lot more attention because it's part of a bigger topic and more people pay attention to that at higher levels. The bad news is that when market research people try to study the PLM industry, their granularity doesn't get down to some of those tiny segments very accurately. Anyway, this is another way of looking at it in terms of the size of companies that are in some way related. have the enterprise software and solutions food chain from the really big players of Apple and Microsoft, and the next layer, as you see there, then the layer below that, where you start to get into the major PLM type companies, then below that, the major MCAE companies, and then a whole bunch of smaller companies that are either independent or are feeding into that. So the MCAE vendors today represent generally that whole clump there, and all these tiny ones down there are the remnants of what one person back, or a number of people back in the 80s called the cottage industry of MCAE. So it isn't all a cottage industry anymore, but there's still a lot of tiny companies out there that have something of value to offer. They're not just remnants that are dying out by any means. Consolidation example, this is a good one. Siemens PLM bought LMS in 2013 officially. It was announced earlier than that, but it took place in January 2013. LMS had acquired a number of companies, the most recent and largest one being Samtec in 2011. Siemens itself acquired Siemens PLM. I couldn't find a picture with 4 fish in it to show that, but that's an example of how bigger companies are absorbing, gobbling up smaller companies. Here's a bunch of further information on MCAE consolidations. 2003 to 2013, you had ANSYS, Altair, Autodesk, Dassault Systems, and LMS all doing significant acquisitions. I won't go into the details of each one of those. The dates are there. There's information on the internet, or you can just contact me if you are curious about any one of those in more detail. ESI, the most recent being Psy Design Labs, Cybernet Systems, a Japanese company, Siemens itself, from acquiring Unigraphics right on through to LMS, MSC doing some smaller acquisitions, and CD Adapco acquiring the smaller optimization company Red Cedar in 2013, and there are more than just what I've shown here. So a summary of the top 8 MCAE vendors, and there you see them listed by revenue ranking. What you don't see on that list, but which I have included in certain other lists that I put together at various times recently, is the MathWorks. The MathWorks is a between 700 and 800 million in revenue, so they're almost as big as ANSYS, but they sort of straddle this zone between MCAE and systems modeling and simulation, and even some other areas like financial modeling and so forth. So do they fit in here, and how much of them should fit in here is an open question. But here you see a summary of recent revenue growth where it's known. You see whether the founder is still in charge, which is an interesting point about the culture of a company, whether they are CAE embedded in a larger PLM company, or whether they're standalone, whether their CAE offering, even though embedded in a larger company, is pretty much standalone in that it's not well embedded with the other offerings of that company. That's what a small X indicates versus a big X. What's their focus solutions? Do they have a focused solution set? And do they have fragmented solution sets? Those are all my personal opinions. They come with a lot of value judgment there, and they're all debatable, but at least that's my call. And the movement in the market position over time here in the last few years. On this particular one, you see that I've separated, I have Siemens PLM in there. Without the LMS acquisition, they would jump up to being bigger than MSC or equal to MSC and Dassault Systems if you include Siemens PLM now, including all the LMS revenue. And then there's this vague topic called thought leadership, meaning even though somebody may rank somewhere in terms of annual revenue, who listens to them and how much do they appear to be shaping the future of MCAE relative to others? And that's where I think Altair stands out as being much more of a thought leader than their current revenue situation would imply. And then some others who are much less thought leadership in the overall MCAE. And with that, that ends my formal presentation. I'd like to thank all of you for having the attention. I hope you're all still there. Again, copies of these slides in PDF form with active hyperlinks are available either, or will be available very soon, through the UberCloud or directly from me, and there's my email address. So with that, Barak, it's back to you.
Thank you, Dennis. Wonderful presentation. We will be taking questions in just a moment. As you come up with your questions, you can type them into the questions bar in your GoToWebinar control panel.